Our next task is to find the absolute maximum and minimum of this function on the intervals shown here. Let's begin by getting all the derivatives, since we will use these calculus tools. The first derivative is going to be minus 2 over x squared plus 2x. The second derivative will have a negative 2 come from this power, which will be combined with the coefficient. So we'll have a plus 4 on top, and on the bottom, x cubed. And here we'll have 2. What we'd like to do is draw a very rough sketch of this function before we even begin to look for the critical points and the inflection points. Let's observe that near x equals 0, this power dominates, and so the function is well approximated by 2 over x. Far from x equals 0, the term that dominates will be this term, and so the function will be well approximated by this quadratic, which will give us a little piece of a parabola opening upwards. Now, it's not too hard to imagine then what this function will look like. It'll basically come down to some local minimum and go back up again. So already we see from our sketch that we're going to expect to get a local minimum. Now let's use our calculus techniques to solve the problem of finding the absolute maximum and minimum for this given function. So let's first find the critical point. We have to solve the equation f prime x equals 0. Here's f prime x, so we're basically solving for minus 2 over x squared plus 2x equals 0. This can be simplified by bringing one of these terms to the other side. So 2 over x squared equals 2x. The 2's are going to cancel, and we can combine the x's on one side to get 1 equals x cubed, from which we can deduce that we're looking for x equal 1. In fact, that's going to be this point right here that we've already identified, and when we look at the second derivative and plug in x equal 1, we get 4 plus 2, which is 6. This is positive, and therefore this tells us that the function is locally concave up, which implies that we've found indeed a local minimum. Now, to find the values of the function that are at the absolute maximum and absolute minimum, what we're going to do is evaluate that function at each of the endpoints of the given interval. So first of all, it's 0.1, and we get this value. At the other endpoint, we get 16.5. Now finally, we should compare these to the value of the function at its critical point, which gives us 3. And now we can identify, by looking at the various sizes of these, we see that this is the largest value, and therefore the absolute maximum of the function on the given interval. This is the smallest value, and therefore both a local and an absolute minimum of the function on the given interval.